Hello everyone. Today I'm going to share you something about our latest project, noise figure measurement for the three-stage S-band amplifier. And in this poster, we measured the noise figure of the S-band optical amplifier based on a combination of two parametric wavelength converters and a C-band EDFA. The noise figures of the three stages are measured separately and used to calculate the total noise figure by the cascaded noise figure formula. To understand this poster, the first thing that we need to know is the motivation. We want to utilize the optical S-band to increase the capability of the optical communication links so we can transmit more information in the same time. There are two types of S-band amplifier in this research area. The first one is thulium doped fiber amplifier. The other one is optical parametric amplifier. However, both of them have an obvious drawback which prevents them from practical implementation in the commercial scenario. For TDFA, the incompatibility of the conventional silica fiber network restricts its application to the fiber laser, which is not sensitive to the complex coupling methods. The same problem of coupling would be a disaster for the optical communication with so many connection points in the system. For optical parametric amplifier, to realize the high parametric gain which is required by the optical communication system, it needs to have at least 10 to 100 times larger pump signal than the designed amplified level, which makes the power consumption and the component quality requirement two biggest concerns of this system. To explore the possibility of alternative plan, which can bypass these two obstacles for TDFA and OPA. A new scheme based on a combination of OPA and conventional EDFA is presented here and verify the noise figure performance by measuring the noise figure of the three stages separately and combined by the well-known cascaded noise figure formula. In the first part, we give a simple explanation of the definition of noise figure. You can check this formula and explanation to understand the big picture of this parameter. Our experimental setup is shown here. We can see in the system is consisting of two OPA and one EDFA. For the first stage, the signal is in the S-band, and we use a strong pump to convert the signal in S-band to C-band, so we can convert the signal to adder in the C-band. Then we will filter out the adder and amplify the adder by a conventional optical amplifier, which is very cheap and easy to get. And in the second stage, we use EDFA to amplify the adder to a strong power level. Then in the final stage, we use the same OPA to convert it back from the C-band to the S-band. Through this process, we amplify the signal in the S-band without require of high power pump in the first stage and the final stage, and we also don't need a very difficult coupling method for the TDFA because we use traditional EDFA. It's very easy to couple these things together. The measurement consists of 5 parts. The first part is the stimulated Brillouin scattering threshold suppression. Why should we do that? Because the biggest limit for the high linear fiber, which we use here, is the power input limitation. And SBS is the most important thing that decides that limitation. So we need to use phase modulation to broaden the spectrum of the pump to reduce the influence of this effect. And in here we discuss some details about how can we do that and how much improvement we can get here. And in the second part, we do the noise figure of the optical parametric amplifier stage 1 and stage 3. And here we give some details about how can you calculate the noise figure based on the parametric amplification scheme rather than the traditional EDFA scheme. And you can check these formulas and we give the experimental result. We use one optical switch to change the input channel to verify the situation when we input signal in the S-band or input signal in the C-band. So through this process, we can measure these things, and we use the single polarization ASE noise extraction and OSA amplification system to analyze the data. And in the search stage, we measure the noise figure of EDFA. We measured the noise figure of EDFA at the normalized amplification gain, which given by the manufacturer. And in the first part, we give OPA quantum limit analysis. This basically gives you the theoretical limitation of the noise figure of this system. You can see here we have our noise figure is a little bit smaller than the theoretical limitation, but it's acceptable due to the drift error of the experiment. And in the final part, based on the experiment we did before, we give a theoretically model to build up how much noise figure we can get when we change the gain of the first stage and the second stage. And through this plot, you can see we can get very small noise figure when we use very strong second stage gain and not very strong first stage gain. So it's acceptable to the low power pump of OPA and high gain EDFA. Through this process, we can bypass the two obstacles we mentioned before and get the noise figure smaller than 6 dB with parametric gain smaller than 4 dB and high EDFA gain. This performance is comparable to the commercial EDFA, so this project can be useful in the optical communication. So that's all for the share of this poster. If you have any problem, you can contact me by sending my email.